today we're going to talk a little bit about so-called functions of several variables. And today's video is just a basic introduction. In particular, we're going to motivate the topic, and we're going to look at how to visualize and sketch functions of two variables. So this is just a very brief introduction to the idea. Now, there's a whole bunch of other topics here. They'll be in the subject of other videos. Okay, so let's motivate the study first. Why is it important to look at functions of two or more variables? Well, our world is an increasingly complex place. And in particular, many phenomena depend on more than one thing. Okay? And if we're going to model these type of complex phenomena, then usually we employ functions of two or more variables. Now let me give you a simple example. In the theory of thermodynamics, the pressure P depends on, of a gas in a cylinder depends on a number of things. It depends on the temperature, the volume, and the number of moles of gas present. Okay, and the actual relationship is given by this equation here. Now, here R is just a constant, and you'll see that this right-hand side is just a function of three variables. Okay? Now, at school or at university, you will have already seen functions of one variable. Okay, so they're of this type. So you learned how to sketch curves for functions of one variable, and you learnt basic calculus, limits, differentiation, and integration. Okay, so the main aim of this section, or this video, is to extend the ideas that you know for functions of one variable to functions of two or more. Okay? And ultimately, we want to learn the idea of a derivative for functions of two or more variables. All right, so why do you want to do that? Well, if we have a basic framework of calculus for these functions of two or more variables, then we can use that framework to more accurately model the things around us. Okay, different phenomena. All right, so what is a function of two variables? Well, firstly, some notation. Basically, we're going to consider functions of the following type. Now, really here, the f is the function, but a lot of people write it z equals f of x comma y. Now, the x and y are the independent variables, and this u is the domain of f, and u's a two-dimensional set here. All right? So this is how we denote our f with domain u, and f outputs a real number. All right? So some simple examples. Here's a function of two variables, and you can see the domain here is just the set R squared. So you can input any x and any y into this function, and it will make sense. Any real numbers, x and y. All right, here's another example of a function of two variables. You see here, the set of points x comma y that make this function make sense is just this set here. Okay, and finally, here's another function of two variables. You can see, well, in order for this function to be properly defined, we can choose any x and y such that the denominator here is non-zero, so that would be our domain. Okay, so even more simply speaking, you can think of our function, of course, is a function machine where you input two values, x and y, and it outputs a real number, f of x, comma y. Okay, well, as a first step to our study of functions of two or more variables, this video is going to deal with visualizing and sketching their graphs. All right, so you can think of this as a first step to understanding these functions of two variables. All right, so to do that, we're going to develop some basic methods. Okay, to do that, we need some definitions. All right, so the first definition is the definition of a level curve of a function f. Okay, now this is just the set of points where the function of two variables equals a constant. Okay, now basically they're just going to be curves in the xy plane. All right, and the set of all points x comma y comma f of x comma y in space for which x and y are in the domain of f, that's called the graph of f. Now, for functions of two variables, the graph is going to be a surface. And when you see this z equals f of x comma y, you think of a surface lying in three-dimensional space. So what does that mean? Well, here's a general picture. You can see I have three axes here. I have an x-axis, a y-axis, and a z-axis. Now, this set down here can be thought of as the domain of f. Okay, it's a two-dimensional set. And then lying above that set is a surface. Okay, now a surface is a two-dimensional thing, but it's sitting in three-dimensional space. Okay, so for every point, say, that lies here in the domain, there's a corresponding point on this surface. Okay? I guess this is really, well, the coordinates are x comma z comma y, and the distance from here to here will be z. Okay, now, note that the z value gives this point's distance, or I guess above or below the xy plane. Okay, here it's positive. All right, so basically, graphs of functions of two variables are surfaces. That's the basic idea here. All right, so to sketch our surfaces, if we're given a function, what we want to do is sketch its surface somehow. And one excellent technique is to employ so-called level curves that I just defined. All right? So in this particular picture, we've got a function of two variables defined here. And these red lines, or red circles, are the level curves for this particular function. Okay, so all you do is you go to your function and you make it equal to a constant. All right? Now, choosing different values of this constant c will produce different circles. Okay? Now, let's say I chose c equals 0. If I rearrange this equation, I'm going to get 100 equals x squared minus y squared, which is a circle of radius 10 and centre 0. So in the picture above, it's this outer circle. Okay? Now, different values of c will give you different circles. All right, so let's have a look at some other surfaces and the level curves associated with them. This one's just drawn using maple. And here, these are the level curves associated with this surface. Now, maybe you can see some sort of relationship between these level curves and the surface. Well, if you slice the surface parallel to the xy plane, these lines will be the points of intersection of the slices. Okay, and here's another one. Here's a surface. Here are its level curves. Now, an idea that's related to level curves are so-called contour curves. Now, contour curves and level curves are basically the same curve, but they lie in different planes. Okay, now basically, a contour curve is just the intersection of a plane with the surface. Okay, so this is actually the level curve, and this is the contour curve. All right, so in that case, what's happened is we've set, remember, we've set c equal to 75 here. Okay, that's how we can produce this particular level curve. And the importance here is that this number tells us how far above or below the xy plane that this curve lies in. Okay, in this case, it's 75 units above the xy plane. That's where the circle lies. All right, so why are these important? Why are these contour curves and level curves important? Well, the idea is used to prepare so-called contour maps when we're looking at mountains and other types of regions. Now, walking along a line, a level curve or a contour curve, would mean walking on a level path. So let's just go back to the previous slide. Imagine this surface is a mountain. Okay? You can see here, if I walk around this path, my altitude above the xy plane stays the same. All right? All right, so let's do an example. Determine the level curves of the following function of two variables. Okay, so the basic idea is the same for these types of examples and problems. You set the function equal to a constant, and then you choose different values for that constant. Okay? In this case, I'm only going to choose non-negative values for this constant, because if you put in a negative number here, you can't solve. I mean, it doesn't mean anything. Okay? So let's put in c equals 1. So if I put c equals 1 here, I get x squared plus y squared equals 1, which is a circle, centre at the origin, and radius 1. Okay, now if I put in, say, c equals 4, I get x squared plus y squared equals 4. Now that is a circle with centre at the origin and radius 2. And then c equals 3, c equals 9 gives x squared plus y squared equals 9. Again, another circle. Okay, so I'm going to draw those circles now. Okay, so that's going to be the top one. The next one. And finally, the outer one. Now I'm drawing these things in the xy plane here. Okay, so this is 1, 2, 3. Okay, well, what do these look like in three-dimensional space? Well, remember, this number here is the height above or below the xy plane that this circle lies in. So this one and this one are going to be the same curve at a height 1. Then we're going to go up a little higher to 4. Okay, so it will be 4 on the z-axis, and then you would even go higher. to 9. Okay? All right. So here's a similar problem, but it's slightly different because we have a square root sign. So does that change things? Well, again, we let f equal a constant and then choose different values for our constant and see what we come up with. All right? So I'm just going to choose c equals 1. I'm going to get root x squared plus y squared equals 1. So if I square both sides, I'm going to get a circle again. If I choose c equals 2, again, rearranging that, I'll get x squared plus y squared equals 4. And c equals 3 gives x squared plus y squared equals 9. So basically I get the same circles that I did before for my level curves. Okay. But here, the c values, remember, are the height above or below the xy plane, right? So this circle will lie 1 unit above the xy plane. This circle will lie 2 units above the xy plane, and this circle will lie 3 units above the xy plane. Okay, so these are the level curves, and these are the contour curves. Okay. Now, note that the f and g from the previous 2 examples, they're different functions, but they have the same level curves. Okay, if they're different functions, then we would expect them to have different graphs. In fact, if we go to Maple and use the plot 3D command, here's the plot of the first function, and here's a plot of the second function. Okay, notice they look similar, but they're different. This one's rounded at the bottom, and this one's pointy, like a cone. So the important thing here is, how can we explain and predict these differences? Yes, level curves and contour curves are good in one sense, but this shows their real limitation. Okay? And the answer is to do with an idea called sections. Okay? Now, sections are basically the intersection of vertical planes with a surface. Okay? And it's usual to choose sections that can involve the XZ plane, the YZ plane and the XZ plane. All right? So let's do an example and see how it all works. We're given this function. We want to calculate the 2 usual sections of the graph of this. Okay, so in the XZ plane, we have y equals 0. So we go up here and we plug in y equals 0. Okay, that then gives us z equals x squared, which is going to be some sort of parabola, okay, lying in the XZ plane. In the YZ plane, we have x equals 0, so we go up here and set x equal to 0, and we get something like z equals y squared. Again, another parabola. So let's just put this all together. Here's our 3-dimensional setup. Okay, I'm actually going to draw S2 first because it's a little easier. Okay, so imagine you're looking down the barrel of the z-axis. So the z-axis is coming out of the screen at you. This is going to be a parabola. Right? Now, for S1, that's S2. Now for S1, imagine we're looking down the y-axis. Okay, so I'm going to redraw it. In this case, the positive x-axis is there and the positive z-axis is there. Again, I've got a parabola, z equals x squared. Okay, so this is S2, our section S2. This is S1, our section S1. Okay? All right, another example. Determine the two usual sections of the graph of this function here, g. Right? Again, setting y equals 0 and x equals 0, we can come up with these curves, S1 and S2. And in a similar way, we get these type of lines here. Okay, so this is going to be S2. Again, I'm just drawing that because it's a little bit easier. This one's going to be S1. All right, so this is something like Z equals absolute Y. Z equals absolute X. All right, so what do we do now? Well, we can take our level curves and our sections and combine them to form our surface. Okay, so how do we do that? Well, the basic idea is to couple the method of level curves with the method of sections. Okay? All right, so from the previous examples, this is essentially what we have. Our level curves were concentric circles. Okay? And the contour curves that were all lying above the xy plane, so we want to pull them up along the z-axis. Okay, now one of these sections, we calculate it to be the following. So what we want to do is combine these two curves to plot something like a surface in three-dimensional space. How do we do it? Well, the circles are bounded by this curve here, and they're all lifted up above the xy plane. Okay, so we can form something like a bowl. All right, so that's our surface there, called a paraboloid. Similarly, if we combine our level curves, okay, again, I'm being a bit rough here with the sketch. I'm only going to draw one section in here. All right. Now, the contour curves associated with this lie above the xy plane because C was always positive. And they're bounded by this V-shaped curve. So putting this all together, we get something like this. Okay, so in this case, we get something that looks like a cone. Now, there are a lot of other surfaces. Okay, there's ellipsoids and lots of other surfaces. But here's an independent learning exercise for you. You should try this to see if you can get a feel for what I've discussed today. So a function is defined in the following way. They want to sketch the graph of this function. Okay, and to give you a little hint, what you should come up with is something like this. Note, this particular picture has a section here, and all you really need to do is work out the level curves. Okay, so that's a little bit on functions of two variables and how to sketch them. Next time we'll talk about partial derivatives.